In this video, we're going to see how we can use reference angles to greatly expand our set of exact output values for our trig functions. So let's consider an angle with a measure of 135 degrees. Now we don't have a right triangle with an interior angle measure of 135 degrees. That's not possible. But we can still think about this angle measure in general. So when looking at this angle measure, we can think of a reference angle. And a reference angle is formed between the terminal ray and the horizontal axis, regardless of what quadrant we're in. So if we look at this terminal ray, and then we look at the horizontal axis, we can think of this angle that's formed between them, which is right here. So we know that half of a full rotation is 180 degrees. So if we swept out 135 degrees, we still have 180 minus 135, which is equal to 45 degrees to go to get to that full half of a rotation. And therefore, this reference angle is 45 degrees. We know a lot about 45 degree angles, though. We already know some exact values for 45 degree angles. In this case, if we draw in, if I zoom in a little bit, and we draw in this right triangle here, we know a couple things. The horizontal and the vertical side lengths for this right triangle are square root of 2 divided by 2 hypotenuse lengths long. So we have square root of 2 divided by 2 for both of those side lengths. And therefore, cosine of 45 degrees is square root of 2 divided by 2, and sine of 45 degrees is square root of 2 divided by 2. So when we go to look at, say, cosine of 135 degrees, then we're actually looking at this distance right here. Cosine of 135 is this distance right here, which is really the length of that horizontal side of the right triangle we drew down here, but we have to pay attention to whether or not it's positive or negative. So in this case, cosine of 135 degrees should be related to square root of 2 divided by 2, but in this case we know cosine, the output of cosine should be negative because the terminal point is actually to the left of the vertical axis. And therefore, cosine of 135 degrees is actually negative square root of 2 divided by 2. It's very much related to cosine of 45 degrees, but we have to pay attention to whether or not we want a positive or negative value for that. Now, similarly, sine of 135 degrees is the vertical component of this angle, which is going to be related to square root of 2 divided by 2, but we have to decide whether or not it's positive or negative. And in this case, since the terminal point is above the center of the circle, we should have a positive output for the sine function. Therefore, sine of 135 degrees is actually positive square root of 2 divided by 2. Similarly, we can do tangent of 135 degrees, which is the slope of that terminal ray, in which case will be, it's also equal to sine of 135 degrees divided by cosine of 135 degrees, or square root of 2 divided by 2 divided by the negative square root of 2 divided by 2, which is equal to negative 1. Therefore, we have some exact values for these three trig functions when the input is 135 degrees. We just leverage what we know about 45 degree angles and then pay attention to whether or not we need a positive or negative value based on the location of that terminal point. Let's look at one more quick example. We won't work through all of these, but let's suppose we have an angle measure of 11 pi divided by 6 radians. So we should draw a diagram of this. So we'll draw our initial ray right here. 11 pi divided by 6 is almost a full rotation. It's a little less than a full rotation. So we have something that looks like that. We'll draw a circle centered at the angle's vertex. And our reference angle here, to get to a full rotation, we still have to go pi divided by 6 radians. So even though our original angle is 11 pi divided by 6, our reference angle here is pi divided by 6 radians. And we actually know a lot about angles that have a measure of pi divided by 6 radians. So we can actually draw in a right triangle here. So we'll draw this in. Based on what we know about 30, 60, 90 triangles, or pi divided by 6, pi divided by 3, pi divided by 2 triangles, We know that this shorter length is 1/2 hypotenuse lengths. The longer side here is square root of 3 divided by 2 hypotenuse lengths, and then we have a hypotenuse of 1 hypotenuse length, which then tells us cosine should be related to square root of 3 divided by 2, and we're going to pick the positive value there. So we have square root of 3 divided by 2. Sine of 11 pi divided by 6 will be related to 1/2. We're looking at the vertical component, but in this case we have a negative 1/2 because the terminal point is below the center of the circle. So sine of 11 pi divided by 6 is equal to negative 1/2. Tangent 11 pi over 6 is going to be related to tangent of pi divided by 6, which is going to be equal to square root of 3 divided by 3. But in this case, we have a negative slope, and therefore, tangent of 11 pi divided by 6 is equal to negative square root of 3 divided by 3. So make sure you see how these values here that we just computed are related to the output of those functions when the input is pi divided by 6. They're going to be very much related. We just look at whether or not we need to change whether the value is positive or negative based on the actual location of that terminal point.